All right, ladies and gentlemen, getting back to it, we're going to have one more example here of how we can actually use percentages or probabilities directly. So we're not saying we have 72 students. They've already gone through and they've figured all the math out, except they know the math of each event. What they want to know is what's the probability that a very specific thing is going to happen. Now, here's what I mean by that. A doctor goes to the office and they can be right, they can be wrong. They can make, in other words, they can make a correct diagnosis and they can make an incorrect diagnosis. But then there's things called like a false positive, where you can test positive for something. So they make a diagnosis, but it's actually wrong. So they were right according to the data they had, but wrong overall with the diagnosis. So it's not just A or B, it's A or B and then A or B being false. So if event A is the person was diagnosed with, in this case, diabetes, then the opposite of that is not that they weren't diagnosed, or the opposite of that is that they weren't diagnosed with diabetes. But then there's a secondary effect. Was that diagnosis correct? So in event A, person has diabetes, diagnosis is either correct or incorrect. So there's a second part to it. There's a follow-up. Nobody gets it right 100% of the time. So we need to find out the statistics that tell us how often does, or even calculate how often should it happen to be reasonable. As a matter of fact, this is how some people get found that they are just not efficient or good at their job, if you want to put it that way. There's a calculation that says people should be 97% accurate or correct in their job. So if you're making something, that means 97% of the time, whatever you're making, it's going to work. It's not going to be defective. It's going to work. So 3% of the time you're good. But if you are found to be making something that is, let's say, 5% of the time is defective, that's outside of that 3% that's calculated. They need to find out, is it human error? Is there a machine error in there? They need to find out why. Because if it can be corrected, it needs to be corrected because they need it closer to 3%, because honestly, budgets are going to be made based on that 3% number. And the more you go over that, the more it's going to cost the company, the less they make, meaning the less they can also pay out. So they can't afford as many employees. It's a long checklist of decisions, and a lot of it is made the way that you're seeing on here. It's the idea that, okay, we make a product, it's either good or bad. And when we said it was good, was it actually good? And when we said it was bad, was it actually bad? And this is how those are calculated, or used, I guess. Not really calculated, used. They already know that 98% accurate, a test is 98% accurate for people who have the disease. In other words, they've done the experimental part. They know that 98% of the time it's gonna give out a correct answer. So that 98% is the idea that event A, the person is diagnosed and the diagnosis was correct. So that also means, where are you? Is 8.3% of people in the United States have diabetes. That means if you go in and you are diagnosed with diabetes, you fall within 8.3%. But that means if you go in that you have a 91.7, I believe it was. Yeah, 91.7. Where are you? You have a 0.917% chance that you will not be diagnosed with diabetes. Now, if event B is that you have a correct diagnosis, not event B, that's what the line over the B means right here. Not event B, it really means that if A is used as a correct diagnosis, that means that not B is an incorrect diagnosis, and you have a 2% chance of being diagnosed with diabetes and it being a wrong diagnosis. Now down here, somebody goes in, they're not diagnosed with diabetes. They fell into the 91.7% chance of people who don't get diagnosed with diabetes. And 95% of the time, that's a correct diagnosis. However, that means that 0.5% of the time, that was a wrong diagnosis based on the test that was given. All right, what does all this mean? Well, we need to be able to use these to find the probability of A and B and the probability of A not B, in this case, to find out what's the probability the diagnosis was correct. And that is our event B. Event B is that we have a correct diagnosis. That actually happens in two different instances. We can have a correct diagnosis when you're diagnosed with diabetes, and we can have a correct diagnosis when you are not diagnosed with diabetes. So how we find that is that overlap. What happens when A and B are correct? And what happens when A not A and B? Because that takes us down the path both times of the diagnosis being correct. Remember, event B is that it is a correct diagnosis, but we have to account for a correct diagnosis that you have diabetes and a correct diagnosis that you don't have diabetes. So I'm going to take this 0.083 because that's the probability of A, and the probability of B after A is at 0.98. In other words, this is saying the event that you were diagnosed with diabetes and the event that it was a correct diagnosis. And we multiply those together. We're going to add in not A, which is a 0.917% chance, and B after A. That means you were not diagnosed with diabetes and it was a correct diagnosis. Well, that's 0.95. When we multiply all this together, you get, I wrote equals, but it's actually about, because we're going to have to round here. It is about 0.952, or you have a 95.2% chance, opportunity, probability, whatever word you want to put in there, it's all the same. You have a 95.2% chance that your diagnosis is accurate according to the test, whether or not you were diagnosed with or without diabetes. You have a 95.2% chance that it is a correct diagnosis.